And I'm going to start the 133 Module 5, the outline refrigeration system. So we're going to take a look at that. I'll pull up the outline. All right. So one of the areas of this particular outline, or one of our competencies, is to explain how refrigerants work within the basic refrigeration system. We're going to get into a lot of the parts and pieces and a little bit of how refrigerants work to some extent. So let's get started with this. All right, so the first area that up till now what we've been doing is we've been looking at using water as a refrigerant, and we've been doing a lot of comparisons to water. So one of the things that we're going to take a look at related to water as a refrigerant is we're going to look at, obviously, its basic molecular composition. Now, water as its molecular composition is actually going to be, obviously, in this case, it would be H2O, as we know. Okay. Now, obviously, its physical states, we can pretty much get, all of them. So we can get, it can be obviously a solid, it can be a liquid, and it can also be a vapor. Any one of those things it can be. So it's an unusual substance. One of the other things is that we call that, or we have a number, an ASHRAE designation number that's considered as R718. And R718 is the ASHRAE nomenclature for water as a chemical composition. Now, one of the things that we also have in here is water has a latent heat of approximately roughly around, whoops, did not like that, so I think I'll write it out. It has a latent heat of approximately around 970 BTUs per pound. Now, it's really an incredibly high amount of latent energy that it has. So it's one of the highest of any of the substances is being around that 970. Now, in the previous chapter, previous module, we had looked at water being roughly in that 970, and it would go up. It would either increase in value or it would decrease in value depending on what the pressure was. So, but the enthalpy numbers always kind of creeped up the higher the temps kept going, and that was due to the freezing point being so stable. The saturation pressure temp relationship that we see here. So, for example, the saturation pressure temperature relationships, typically when we do that, what we're looking at is very much like you did in the previous one, where you would say, okay, well, find out what the pressure is, and you would go find out what the boiling point would be from there. So we basically used what we call a steam table. And that's what you end up doing in the previous chapter, previous module. So it's pretty straightforward to find out what that temperature pressure relationship is. But we definitely knew that was going to be one of those. Now, one of the things that we do have as a limitation with water, and that is one of the problems that we run into. So with water, one of its limitations as a refrigerant is that it does indeed freeze at 32, and it is somewhat corrosive. So that's a little bit of a problem for most systems. So when we get into our bigger, larger commercial jobs, what we find is most of the jobs we have to actually, to prevent the corrosion from being a problem, we have to use some sort of a chemical treatment to prohibit any type of corrosion within the systems. And that's true of water boilers and you name it. So those are all systems that we have to generally do. Our chilled water systems, it does apply to that, but in many cases that's what we end up doing. So that's a little bit on just on the water by itself. So let's take a look at refrigerants and specifically we're going to take a look at one of them in particular that we're going to use. So the first one that we're going to take a look at is what I'm going to call refrigerant 22. And refrigerant 22 has a, let's call it somewhat of a different molecular composition. And its molecular composition is going to be illustrated to the right here. And what this one is, if we look at the name or the nomenclature, there's some key words in here. And I'm going to switch to a green color here for the sake of doing this. One of them is, in this case, monochloro-difluoromethane. So it has essentially a single chlorine atom. It's got 2 of the fluorine atoms that are in this molecule. It also has some hydrogen, and it also has some carbon. Every one of those is essentially part of that process of what we have. So if we look at the composition or in the nomenclature to some extent, you'll notice that we've got your CHC, Cl, I should say, CHClF2 is what we have, or refrigerant 22. So refrigerant 22 is the one that we'll be looking at specifically. Now, let's talk about physical states. So specifically, there's only 2 ways that we're going to really run into on this one. So the physical states, as a general rule, is we're going to see this as a liquid, or in some cases we'll see liquid, or a vapor, or both. And it could be, it's either liquid, vapor, I'm going to say, or both. It could be a combination of the 2 depending on where we're at. Obviously, from the last chapter, you probably realize that if you are if you're at saturation, you could probably be both as a general rule. So if we are in a subcooled state, then of course we would be in a liquid. So, and of course if we're in a vapor, then we would almost guarantee that we're probably superheated. And again, if you recall the different terms that we had utilized, we had used terms like subcooled liquid, saturated vapor, saturated liquid, superheated vapor, or it could be a combination of the 2. So those are the different things that we had. Let's take a look at the next part. So the latent heat. Latent heat for refrigerant 22. A lot of the refrigerants that we use in our industry don't have the incredible amount of energy that you saw up in water, using water. So the latent heat that we typically saw in these or that we typically expect to see, like in refrigerant 22 as an example, they're around 100. Right around 100 BTUs of energy per pound is a ballpark number of what we'll use. Now, obviously, we can figure out specifically what would happen. Without a doubt, we can figure that out and using some of the pressure enthalpy tables as an example. All right, so the next thing that we're going to take a look at is called the saturation pressure temperature relationships. And this should not be anything new to any of you. The saturated pressure temperature relationships that we typically are going to deal with is going to have to use some sort of a table, a reference. That's normally what we'll end up using. So what we're going to be looking at is one of the handouts that I had given everybody the last class was we are going to be using what we call a pressure temperature chart, or we'll sometimes call it the PT chart, is what we're going to be looking at. And that is one of those that we'll be typically dealing with to try to figure out where that's at. Now, I'm going to pull up to show you exactly what that is. I'm going to go back to one of the handouts, and I'll come back to that. Is one of the handouts. So, for example, the one that I handed everybody is essentially going to be the pressure temperature chart. So this is what we refer to as a pressure temperature chart or a PT chart. And it's going to identify a certain temperature, and it's going to identify a certain pressure. And I'll go through this a little bit with you a little bit later in the module to get into some of the details of that. So let me go back to this. So what are some of the advantages of refrigerants? And you know, what benefit do we get out of some of these? So for example, the first thing that I would get into is with refrigerants, I think one of the things that there are advantages of some of these refrigerants, I would say, would be, you know, you have different compositions that can be produced. There are many different types of refrigerants. And for example, I would say one of the benefits or one of the advantages that I think we see in a lot of these is that you can create, let's say, for example, refrigerant 134A as an example. And it might work better. So for example, it might work better, and I'm going to just pick a few notes, that some of them maybe work better for low temps. And you know, you could say some of them might work better in high temps, and there's a number of them. And so what I have, the point I'm making is that they can create all these different chemical compositions, and they will specifically try to do that for the sake of creating these substances that will give you these certain pressure temperature relationships to give you the most BTUs that you can get out of this substance without creating any harm to the system. And I think that's one of those advantages that I would see. The big thing, one of the big things, and again, this kind of alludes to the next one. It says, you know, there's different temperature pressure relationships for different applications. So for example, if I have a low pressure or a low temp application, I probably want a refrigerant that's going to have, let's say, a higher pressure. And I want to try to make sure I'm using something like that. So for example, in our industry, if you're dealing with a freezer, there's a very good chance that you would likely be using maybe refrigerant 404A, and maybe not necessarily R22. And if we were, and what makes that such a good refrigerant is the fact that it gives me a temperature range that yields me pressures that always stay above zero, where I'm not putting it into a vacuum. So those are examples of that. If I have, let's say, an air conditioning system, I might use refrigerant 410A in a residential building. Now, what makes that such a good one? Well, they've developed a composition that yields me pressures that are fairly good, that are fairly stable, that don't create system problems for me, such as they don't have a ton of fractionation or different types of things that are going on within the system. But everything that, all of these refrigerants, they basically have some sort of what I would call, they have a specific numbering system. And what the main thing that really gives us some information about the refrigerants is when ASHRAE creates this, let's call it this R system or this refrigerant designation, what they are doing is that particular R system, whether it's R22 or R134A, that R dash, let's say something, 134A, 410A, 404A, or 507, whatever it might be, it's that number is what really counts for our system. So that's what tells us more information about the refrigerant. So one of the things that it does is it'll every one of these numbers, so for example, the first digit will have a certain meaning, the second number has a certain meaning, the third number has a certain meaning, and then there will be a letter after that will have a meaning. We'll get more into that a little bit later, but I think the point that I just wanted to make at this point is there's a logic to the madness of refrigerants. It shows, hey, we've got this refrigerant, whether it's R22, it has a meaning. All right, so let's talk about some of the appearance of these refrigerants. So the first thing that we have in there, generally most refrigerants are very clear. Most of them are very, very clear. Not clean, okay. There we go, clear. So most of them are very clear, and I would say they're very similar to water. They look a lot alike. Dirty refrigerant in a system will be very dark, but if you look at water, water can be super clear or it can be very dirty depending on the level of, let's call it, things that you don't want in there, some dirt, some contaminants. The pressure-temperature relationships. So earlier I talked a little bit about, how we use a saturation table or a pressure-temperature chart. Well, every one of these refrigerants that we deal with, they have a certain pressure-temperature relationship that tells you the saturation. So what they're telling you is it's saying this is where the pressure or the temperature is at this saturation point, whether it's the saturation temperature, and it always is giving you that of a liquid vapor mix as a general rule. Now, we can get a little deeper in that. Technically, if we look at a saturated liquid in a pure substance, it will be that of, it'll have the same one unique pressure temperature relationship of a saturated liquid. And if it's a saturated vapor, it has a specific pressure temperature relationship. Now, and sometimes they're the same, sometimes they can be slightly different. That is one of the complexities of that. When we look at the pressure, the PT chart that you had handed out, you'll notice that they have many, many different refrigerants that are shown, whether it's 401A or 402A, and they all have a different pressure temperature relationship that we utilize as we do this. So pretty neat. All right, so let's take a look at some of the safety devices or safety parts of refrigerants. So refrigerants, as a general rule, can be very safe if handled correctly or if handled appropriately. So, for example, it is certainly a bigger one. One of the big things that we really have to pay attention to with refrigerant density is refrigerants are indeed heavier than air. And why that is so significant is that it tends to create a problem for a technician if you are working in an area and you have a refrigerant leak. A very large leak will basically drop right down to the floor and displace a lot of the oxygen, and it becomes a little bit of a problem for us. So you really want to be very, very aware of that. So refrigerant safety is a big concern for every technician today. The first sign, they talk about the first sign of inhaling of a refrigerant. So when I look at a refrigerant, one of the first signs of inhaling a refrigerant is lightheadedness. And so you wonder, well, what's the deal behind that? Why is that? Well, one of the areas that you run into is that if you do breathe in a high percentage of refrigerant, what it will do is it will get, let's call it, inhaled in your lungs. Your lungs would have an inability to push that out. Now, a very large leak in a system, the way your breathing works within your own body is as you breathe refrigerant in or breathe oxygen in, your body would exhale carbon dioxide, and that's a kind of a product of respiration. What happens when we breathe in refrigerant is that you don't have that ability to push it out sometimes if it's excessive enough. So there are some times where you'll get a system that will have a leak, a very large, let's say a line were to rupture in a job that we would have issues with, and a line breaks, and one of the problems you run into is that the refrigerant will displace so much of the oxygen in that area that you probably won't even get out of the room, most likely. Now, I had an old timer that I remember from about 20 years ago that had taught here at some time, and he taught a lot of classes that dealt with ammonia and a number of things. Well, this gentleman was telling me a story about one of the mechanic rooms that he was in, and that mechanic room had one of the lines rupture. And this is a guy that I would say is probably about 300 pounds, not heavy. He's a 6'5", 6'4", big guy. And he was telling me the story. He said they had to come and drag him out. He said they couldn't move. It happened so fast that he had no idea what happened. Just literally, the line broke. It displaced so much of the oxygen. Before he knew it, he was on the floor, and of course, thank goodness he did survive. But there are people that indeed don't do that. I remember quite a few years ago, one of the things that the refrigerant tanks would do is the refrigerant tanks used to be able to refill them, and I know people that used to take refrigerant 22 and refrigerant 12, and they would use them to fill up inner tubes. It was an easy way. You just put it near the valve and it would blow it in there. Well, I knew people that, or heard of stories, I should say. I don't know anybody who personally did this, but I've heard of stories that I remember from years ago. One of the national television stations had done an episode of people inhaling refrigerant accidentally and filling up air mattresses, for example. And then they would jump on the air mattresses, and when you get a leak or a rupture, if you were low enough, let's say, for example, in a tent, people would inhale it after this large leak when the thing would rupture, and they couldn't breathe. So it's a major issue. We're fairly careful with it, but accidents can happen, especially if you're in a small enough area, small enough room. So you really have to be careful. Obviously, it can quickly proceed into death if it would be sustained and you couldn't get rid of it. So most everybody would pretty much tell you to leave the area, evacuate it, get some fresh air, ventilation. Those are the big things on there. So it's one of those things that you really just have to be aware of. In small levels or small amounts, most refrigerants are fairly safe, but there are some that are not. So refrigerant density, that was the main thing here, just recognizing heavier than air. It's a major deal definitely if you're in a small area. So let's look at item B. All right, so on item B, we talked about, we're going to talk a little bit about the toxic, let's call it decomposition of refrigerants. And what is it exactly what that means? So when we have refrigerants in a system, and let's say we put a torch to it, maybe we're going to braze a line, or we're going to use a high temp type system that's going to, let's say, try to repair a line, or we're going to put a service tap on a system. One of the things that happens is you can have what they call a decomposition of the refrigerant. And what it will do is it creates almost a nerve gas, like what we call phosgene gas. And there's actually, there's three vapors that can be produced whenever we have a flame or we have a very hot surface that would be in contact with refrigerants. And it'll break down into what we call phosgene gas, and as well as hydrofluoric acid vapors. And they don't have a very pleasant odor, and they're not real healthy for you, as you can imagine. But those are things that you definitely want to make sure you take precautions to it. Now, every technician has to be somewhat concerned about this, because and I've repaired lines before, and as I'm warming up the refrigerant lines, I can see that there are refrigerants that are coming out of the system. And even if you are taking nitrogen and you're putting it in your refrigerant lines to sweep the refrigerant out of the lines, if you're torching or you're using a torch and it's coming in contact with those refrigerants, you'll actually notice it by the color change. Whereas if you burn nitrogen, you don't recognize any change in color, it'll be clear. But if you burn refrigerants, it almost always will turn green. And so it's a little bit of an issue that a person has to be aware of. So usually I can tell this by, let's say by the color, by the color change on there. So obviously I'll just make a note of that here. Color changes can indicate refrigerant. Now, the color changes that I'm referring to this is on an open lines. So on an open line, you're going to notice it. On a closed line, you'll never see it. Inside copper, you're never going to see it. So that's kind of one of those that I would identify. They always will tell you. They always will tell you. You do all these service practices in a well-ventilated area, and that's the reason why. If you got a high accumulation, it cannot be good for a person. So that's kind of the one thing. All right, so how about, so what do we do? So move away from the fumes quickly. And one of the things that has to be a concern for us is if you are not moving away from the fumes, as you see that, obviously that's telling you there's, that if you're recognizing, let's say, a color change, or you're recognizing maybe an odor that isn't pleasant, that would be one of those things where you'd want to make sure that you're displacing those refrigerants. And they talk about the fumes breaking down quickly if the heat is removed. So, in other words, if you are if you pull the heat away, you'll notice very quickly that a lot of those odors kind of dissipate into the atmosphere. If the concentration is high enough, then clearly you won't even recognize that. So that's would be a concern on there. So you have to be a little bit cautious on there. So this is a big thing from a safety perspective is, hot flames, big one here, hot flames, hot surfaces, they will break down into these three substances on there. So, and hydrochloric and hydrofluoric acids will eventually lead to like compressor motor breakdown, those types of things. The gases, phosgene gas, obviously that name comes to mind because during the Vietnam War they used to use nerve gas, and phosgene gas was one of those that they had talked about quite oftentimes. So let's take a look at the next part of this thing. So the next safety item that we have to deal with, which is also a big one, is going to be frostbite. Now, one of the things that concerned us with frostbite is the fact that probably the biggest thing you're really worried about is your eyes. So if something were to happen where you had refrigerant, especially liquid refrigerant, that would make it in your eyes, it would almost inevitably cause blindness, and that would be an issue. So the big thing the person has to really have is with eye protection, obviously, and that's one of the reasons why when we deal with in class, safety glasses, and obviously that would be a concern for everybody here. And for let's say if you have a refrigerant line that were to break, so it's a little bit of a concern that you would have to kind of be aware of. All right, so the next thing that we'll look on to some extent is they talk about treat spring refrigerant like a flame and move away. So what we mean by that is, for example, if you happen to have a system that would happen to have a line that would break, or that would have a leak, maybe a crack in a refrigerant line and it's spraying out liquid, get the heck away from it. Just leave it be. Don't try to stop it. Don't put your hands on it. Don't do anything like that would create a problem for you. And that's something that you have to be a little bit aware of to prevent any type of hazard on there. So I do want to show you an image, and it's not a real great image to want to show anybody, but it's fairly telling to see that. Oops. Let me take a look at. Okay, so excuse me. Let's go back to that, and one of them that I'm going to show you. I've got an image. This is in one of your handouts. So if you want to take a look at handout 133 M537. Now, here's an example of one of the of one individual, and I've got a couple other pictures, but I didn't put those in this handout or anything like that. But here's an individual. What happened was he had this individual happened to have an issue with a refrigerant burn, and what happened was some of the liquid refrigerant was spraying out and kept spraying out and kept spraying, and it literally burned. It gives you kind of this burning sensation, and it's literally kind of boiling your skin off is really what it's doing, and almost like a frostbite on there, but very, very concerning that you have to really watch that. Now, I've seen individuals that have had major burns, and what they have, trying to stop refrigerant leaks. So I had one guy that had, he had a line, one of his lines broke off of the system. He tried putting his hand on it to stop the refrigerant. I'm like, oh my God, leave it spray out. Just kind of move away, let it be. And his hand was all purple from just the frostbite, and it's a major deal on this. So the bottom line is this: if you ever run into this situation where you happen to have a system, whether it's here or whether it's in the field, and there is a leak, don't try to stop it. Just let it leak out. Get out of the area, get out of the way, make sure you ventilate, make sure it's all good before you get back into that. And that's probably the best thing that that anybody can kind of do on those types of things. Okay, so let's talk a little bit about, so I really can't emphasize this enough about, treat a spraying refrigerant like a flame. Get away, don't try to stop it. That's the reason behind that. So I'm just going to put a note on here to see handout 37. Okay. Well, how about environmental safety? So, environmental safety. So, one of the things about refrigerants that's, I guess, not such a good thing. For quite some time, they have known, this has gone back really in the 60s and 70s, they already had this kind of recognized that they were suspecting that refrigerants were creating a problem with ozone depletion. And what happens is what we call stratospheric ozone, the purpose of that is that the ozone that's in the sky or in the environment, in the stratosphere, is intended to block UV rays. And that's, the UV rays are, the concern with the UV rays is obviously when we have issues like that, it can cause, increases in human health issues, increases in cancer, increases in eye disease, a number of those types of things that it can be causing. It also creates some environmental issues, such as one of the things that happens is you get a decrease in production of the photosynthesis problem is issue, not really a problem, but you get reductions in the levels of production in crops. So in other words, you might see some levels of deforestation, or you see certain crops that don't grow as well. So the ozone layer is one of those things where they like to keep that. So health and environmental are some of those issues. Now, my intent is not necessarily get into that in deep level. We actually do talk about that more in your next refrigeration class, where you'll be getting the EPA certification that will get deeper into that. And there's some information in the textbooks that will go into that. And I'll be assigning some chapters in the fundamentals book related to that. But very important to recognize that. The chlorine molecule, part of the problem and how this happens is we have certain refrigerants that are called chlorinated refrigerants. And so you might have noticed in R22 there was some chlorine in it. So the chlorine atoms, or we'll say chlorine atoms within the molecules, they actually will create and destroy that ozone layer, is one of the things that goes on there. So the chlorine molecule is really kind of the problem, or the chlorine atom is kind of the issue in the ozone. And one of the problems you run into is that chlorine molecule is a repetitive process. So one of the things that happens is when the chlorine molecule breaks down, that is, it breaks, let's say the refrigerant is escaped into the atmosphere. The chlorine atom in that substance will create a substance, oftentimes that's called chlorine monoxide. And what it will do is the chlorine atoms will go ahead and grab and attach themselves to part of the ozone, let's call it an ozone molecule, creating a substance called chlorine monoxide. And that particular issue creates a stratospheric problem. And when that breaks down, it kind of creates a repetitive process where it happens over and over again. They claim that one chlorine molecule will literally destroy up to 100,000 ozone molecules. So it really is a major concern, which is really what's leading a lot of the change in our industry related to that. So let's hit up on the next part of this environmental safety, and one of them is obviously, what are the rules and what can I and should I and shouldn't I do? Well, certainly venting of refrigerants is illegal, and it does hold technicians, it holds companies. They have to be, they can be held actually personally liable and responsible. So they can be fined, they can lose their license, they can any type of certifications, they can lose those types of things. So it's a little bit of a, there are rules and laws that have to be done. Now, policing it is a little bit of an iffy thing, but it's one of those where it depends on who you're working with. There are some, many people by now, because this has been going on for the last 40, almost 50 years here that we've been dealing with this, people are aware of some of those rules. They recognize that you can't just open up and cut the lines and let all the refrigerant vent out. So it is one of those things. So what if you do have this unintentional release? What happens if something happens? Hey, I was working on the system, the line broke. Well, they call that somewhat of an unavoidable release. Sometimes what we'll do is if refrigerant is just, you didn't have any, you had no say in it, and it wasn't something that you intentionally did, they don't really create a problem with that. That's allowed. I'm saying it's allowed, but it's called an unavoidable release. You couldn't help it. It was going to be what it was going to be. We oftentimes use a term in our industry that's called de minimis. De minimis release. And de minimis, it's a minimum amount of release that you can happen. So I don't know, hopefully I spelled that correct. Some of the other rules that we have to do is companies, technicians, they have to be registered and certified to handle refrigerants. So what this means now is that anybody that purchases, anybody that installs systems, anybody that works with systems, they have to be certified to handle that. They've got to, I can't go to a wholesaler and buy a drum of refrigerant to work with our systems unless I show them my card. They're not supposed to sell it unless they have that card. So it's one of those where those wholesalers can be held liable if they sell it to somebody and they find out, hey, you sold it to an uncertified technician. That's going to cost you $100,000. And, obviously there aren't very many companies that can handle those types of losses. So the next thing that I want to hit up on is refrigerants. And refrigerants are what they call a greenhouse gas. Now, what does that mean? Well, what it means to some extent is every refrigerant has what I would call a global, or what I'm going to say is a GWP. and it's a different a type of a rating system than ozone depletion. It's two totally separate things. So when they say refrigerants are greenhouse gases, it contributes to something that's called global warming potential. So that's GWP, global warming potential is what that refers to. So what happens is with refrigerants tend to create a problem where the refrigerants, when they get released into the atmosphere, and you got to remember, for many years prior to a lot of these rules, a lot of our refrigerants that we're using in our industry were just vented off. I remember early in my career when we worked on a system and there was a problem with that, we would literally vent out all of those refrigerants instead of recovering them. Recovery wasn't really even a rule or a regulation. So, all right, I'm going to work on this one. You just vent off what you're dealing with. So it's it's another process that they use. So it's really not until really the mid-90s when we started to have the requirement where you're really required to do that. So it's been some time now. So, but global warming, what happens with these is when you get all these refrigerants that were vented, what happens is those refrigerants tended to, what happened was the refrigerants tend to trap these gases. So in other words, one of the things that they're worried about is with, let's say, the carbon dioxide from automobiles and carbon dioxide from a lot of let's call it contaminants, a lot of pollution. What it tends to do is it tends to cause those molecules to not, let's say, get up into the atmosphere and be dissipated completely. And what happens is the refrigerants tend to kind of hold and not allow the heat from the earth to tend to make its way out into the troposphere and stratosphere. And so one of the issues that they run into is it tends to lead into global warming. Now, this is one of those controversial topics that not everybody is in belief that global warming actually exists. There's certainly scientists that say, yes, it absolutely is happening. There's other people on the other side of the fence that say global warming is just simply something that's going to happen. The scientists claim that if they look at the data from the amount of refrigerants that are used for the last 100 years, and you look at the temperature of the oceans and the amount of destruction that has occurred, it's very, very obvious of what's happening. That there's definitely some warming that's going on. There's been excessive changes that have occurred with relationship to that. But there again, very, very controversial. So that's one of those things where there's two trains of thought there. All right. Okay, so let's take a look at the last few things here, and the next one I'm going to get into is essentially basic components of refrigerants, and I'd like to identify 3 different refrigerant types. One of them is called CFCs, and with CFCs, CFC stands for chlorofluorocarbons, and these are, I would say, these are the worst of the refrigerants that are used because they contain a lot of chlorine, and this was the big one here that was really the problem, is I'm going to highlight chlorine. But one of the problems you run into is the chlorine is the big culprit for a lot of that ozone depletion, issues. And so that's really the big culprit. The CFCs by far had the greatest and the highest concentration of those substances that we had to worry about. Now, these have been completely phased out. And they were phased out, I would say, back in, they phased them out back in the I would say the late 90s, like 1995, end of 1995 to early 96. So the rule is that essentially based on about 1990, January 1, 1996, you could no longer produce those, and so anything that was used, it was really just things that were already produced. There was no production at all, and I'll just put that date on here. I guess it's for what it's worth. The date on here is, I would say, phased out, and I'm going to put on here January 1st, 1996 is when they phased it out. So that's one of those. So what are some examples of that? And for example, one of them would be refrigerant 22 as an example. And so that's one of those things. I don't know. I don't like this new version that they have here. Oops. Let me back out of that. I got to figure out how that update works here on these iPads. So some examples. Whoops, I did not mean to say 22. That was a mistake. R11 is one of them. Refrigerant 11. Another one would be refrigerant 12. Now, refrigerant 11 is basically a low temp refrigerant or a low pressure refrigerant that we use in water chillers and a lot of large chillers. It's not a common refrigerant. We actually used to use R11 as a cleaning agent even in refrigerant lines, so it had a lot of really good uses, but it had a high level of concentration of chlorine in it comparative to some of the other refrigerants. Refrigerant 12 was right along with it. It's not a great refrigerant to use, but you might remember if you have an older car, refrigerant 12 is actually used. Refrigerant 12 is one of them that was used in that. So like all your old cars, anything prior to, I would say, really in the early 90s is when they started to shift that over. And even home refrigerators, almost all the home refrigerators used to be R12, but then they switched it to 134A, just like the cars. So there's a couple of examples. Another refrigerant that was used in our industry is R500. And R500 was a refrigerant that we used in some of the, in certain air conditioning systems and low temp refrigeration, just as R502 is another one. And those are all typical examples. Now, one of them was refrigerant, one of those was, I'm going to make a note on here. Those were all of those refrigerants have all such been phased out. And one of the things that we are, that obviously you can't buy those anymore, pretty much are, if you have any application for them, you have to do that. But part of again, the biggest reason is, I'm just going to make a note on here, these all have the highest levels of chlorine. They're very bad. I would just say they're bad for the ozone. So bad for the ozone. All right, so let's take a look at the next refrigerant that we have to contend with and deal with. So this next one here that we deal with is item B, is the HCFCs. And they have a little bit of chlorine. They're not terrible, but because they do have some chlorine, they were on the phase-out list. Now, these were refrigerants that, when we say they're being phased out, there was a major reduction. So there was a major reduction in the production in 2020. There was a major reduction of anybody producing HCFCs in the year 2020, which is where we're at right now. And that particular reduction, it was fairly substantial, and these are all based on what they were producing and back really into, I would say, levels that were, from 15 years ago is what they were doing. Now, the next thing, the complete phase out will be in 2030. So, and obviously, I'll make a note of that here. 2030, total phase out. Whoops. Total phase out. All right. So those are some of the rules. What are some examples? They're not as bad for the ozone. That's one of the big things. So I'll just put a note on there. Not as bad. Okay. Some examples. The most common one that comes to mind, refrigerant 22. So we call that R22. And refrigerant 22 is an HCFC. Another one is R123. That's another one of these. Now, those are two examples. So R123 was kind of the replacement for R11. So all of these guys out in the industry that had chillers and low temp or low pressure chillers, they were actually using refrigerant 123 as the replacement. But there are some issues and with that. So and this has been going on for quite some time. A lot of the manufacturers have been trying to figure out, is there a better system? Is there another refrigerant that we should be using? And they obviously had to try to develop that and make that indeed happen. So those would be some examples of that. But again, not as bad, but they are, it's just got less chlorine is the way I would say that. So it has less chlorine. Not completely, just less. Okay. And the last one of the bunch that we have. Now, I actually could add another row of refrigerants, and I probably will in this case, is what I'm going to try to do. So one of the things that the next one that we're going to deal with, which is what I would call this as HFCs, are called hydrofluorocarbons, and they don't contain chlorine. Now, that's interesting that they do not contain chlorine, which means that they should be completely safe for the environment. But that's not entirely true. They don't contribute to I would say the ozone to depletion problem, but many of those HFCs have fairly high levels of global warming potential, and I would say in some cases higher than what the other types of refrigerants were, whether it was HCFCs or CFCs. So it's kind of a little bit of an issue to contend with. So what are some examples of this? So most of the refrigerants that are used nowadays actually are HFCs in current equipment. And I'll give you an example of one of them that I would say is, let's call it R134A is one example. There we go, R134A. That's one of them. Another one of those, and obviously R134A is one that you all see used in your automobile. Another one is R410A, and that's used in a lot of the air conditioning systems that we would use in there. And those are all examples. And here's the thing, is that almost every one of these new refrigerants, and I could throw some other ones in here, another one that's used, that we're going to be using in class is, whoa, what happened there? I wiped it out here. I guess I better rewrite that. So one of them is going to be R134A, R410A. We have R404A. And R404A, we have some trainers that will use that in the lab, and those are so both of those two are in there. A lot of ice machines use these types of things, so those are all things that are kind of happening in there. So let's take a look at some of these to some extent. Almost every one of these things is, I'm going to call it the R400 series refrigerants. So the R400 series refrigerants are going to be such that those are going to be the refrigerants 134A, 410A, 404. All of these fit into that HFC category. I'm going to add another one of these, and I want you to add this on your charts. I'm going to see if this will work on here. We're going to add an item D. And item D is, we'll see if that shows. Nope, doesn't want to show that. So here's how this will end up working. So an item D is, I'm going to call this one, let's see if I can get this to go. And an item D, we're going to call this the hydro or HC refrigerants. There we go. HC refrigerants. Now HC stands for, let's call it hydrocarbon. Hydrocarbon. So hydrocarbon. And hydrocarbon refrigerants, as a general rule, hydrocarbon refrigerants are the types that we would normally use, and I'll give you some examples of that, and you actually might recognize some of these. So one of the hydrocarbon refrigerants is actually going to be R-290. Now, you might say, well, how in the world would I ever know what R-290 is? R-290, is actually propane. You might have heard of propane before. Propane is one of our gases that we use. So if you have a gas grill, that's an example of that. It is not the same. We're talking about R-290 or propane as a dedicated refrigerant for that. So it's refrigerant grade, I should say. There's different grades of propane, and this is one of them. I'm going to give you another one. Another one of the refrigerants is called R600. And R600 is one that you're probably going to start to see more of that in our home refrigerators and home refrigeration. And surprisingly enough, that's actually called butane. So there are refrigerant grade, butane and propane. So if any of you have ever heard of a Bic lighter, Bic lighters contain butane in them, and it's of course not refrigerant grade, but it has those characteristics. So these are all refrigerants. Now, can you think of anything wrong with using hydrocarbon or HC refrigerants? I probably can. I can think of one thing that would come to mind specifically, and these, I would say, all of them are flammable. All of them are flammable. So that's kind of a little bit of a problem. So can you imagine going on a service call with a flammable refrigerant, and you're trying to do, maybe you're going to braze a line, or you're going to do some process where there would be a spark, and it really creates some service issues for us. So that's kind of one of the concerns that we would have on that. So it's pretty major. So, all right, we're going to, so what I'm going to do is this. I'm going to stop the recording, and then I'm going to get into I'll do a smaller little mini recording about finding saturation temps and condensing and evaporator temperatures to be able to do this. So that will conclude this system up to number 4 for that, and I'll deal with 5 and 6 in a separate video.